Second video on simplifying radical expressions containing variable expressions on the inside, but essentially we're going to do the same principles that we explored in the last video, which is we're going to remove any perfect nth roots out of each of these radicals, and we're also going to rationalize if necessary. So looking at this first expression here, again, I always recommend that if you have a coefficient in here, some numerical value, you write the prime factorization of it. So we could say really just 5 times 1. So 5 to the first, we can leave it that way. So we say 5 to the first, a to the fifth, b to the ninth, c to the 13th. The reason why this is not in simplified form is because if we're taking the fifth root of something that's bigger than 5 here, then that means that we have perfect fifth powers in here. So what we could do is instead rewrite this, extracting any perfect fifth root. So we say, well, first of all, I had 1 5. So could I make a group of 5 5s? Well, obviously not. So we're going to leave that 1 5 on the inside. We say a to the fifth. Now that's nice because I'm taking out groups of 5, so I can make one group of a to the fifth coming out. And we say that there would be no a's left on the inside. Technically, we could write a to the 0, which is 1, but it's not a necessity, okay? So we say b to the ninth. Now here's the thing. If I had 9 b's, I could make you one group of 5, but there would be 4 left over on the inside. You can see how this was not enough to make a perfect group of 5 here, a perfect fifth. Then we say, well, c to the 13th. If I had 13 c's, and I'm splitting them up into groups of size 5, I can say, well, then I can make 2 groups of c to the fifth here. And they'll leave behind, 2 groups of 5 is 10. They would leave behind the other 3 c's on the inside of the radicand here. So my simplified expression is abc squared, and then this would be times the fifth root of 5b to the fourth, c to the third. And we can tell that this is simplified because there are no perfect nth roots in here. You can look right at their exponents and see that. And we don't need to rationalize. So here's our simplified form. So take a look at this next one here. We know our properties of radicals say that we could actually split this up into the cube root of x. I'm going to write x to the first over the cube root of y to the 7th. Now here's a few facts about this. First of all, up here we don't have any groups of 3 we could remove out of this. We say x to the first, that's hardly enough to make a group of 3. But on the bottom, we see that we could actually extract some perfect thirds here, cube roots. So we say, well, if I had 7 y's, I can make you 2 groups of 3. So we're going to take 2 of those groups of y, put it out front, and rewrite the cube root of now, this would be y to the first left over on the inside. And this is still on top. We still have the cube root of x to the first. The thing about this is we can't leave this cube root of y to the first down here. So what we need to do is we need to rationalize this. That is, we are going to multiply the top and the bottom times the cube root of something, all right? But here's the thing. We only want to put in enough y's to get this up to be big enough to be extracted out of this. So if we had 1 y and we need a group of 3, basically we're only going to build in 2 more y's because that's all we need. So now, using our properties of radicals, which say that if you took a cube root times a cube root, you can go ahead and multiply the stuff on the inside. Well, the inside of the top here is going to be x to the first times y squared. So the cube root of xy squared, and in the basement, let's keep this in mind, we still had a y squared right here. But when we take the cube root of y to the first times the cube root of y to the second, you actually get, this is just side work here, you get cube root of y cubed, but that's just y. So those cancel out and become just a y. So our simplified expression now is this. We have y cubed in the basement, and the cube root of xy squared here. So again, we have no perfect, you can see no perfect cube roots up here, and we have no radicals in the basement. So this would be simplified form right here. Cheers. Simplified form.